Hi everyone. Today we are going to talk about section 3.4, derivatives as rates of change. In this section, we interpret the derivative as the rate of change of a function. This idea is very important because derivatives are used to describe how quantities change. For example, in physics, derivative describes velocity and acceleration. In biology, they help model population growth. In economics, they are used in marginal functions, such as marginal cost and marginal revenue. So the derivative is not just a formula. It is a way to measure how quickly something changes. Now, let's quickly review the idea of amount of change. Suppose we have a function f of x. If we move from x equals a to x equals a plus h, the amount of change of the function is f of a plus h minus f of a. This simply measures how much the function value changes between those 2 points. If we divide the change by the change in x, which is h, we get the average rate of change. We have already seen that this represents the slope of the secant line between the points a comma f of a and a plus h comma f of a plus h. But often we want the rate of change at a single point, not over an interval. To find that, we let h get closer and closer to 0. When that happens, the secant line approaches the tangent line. This gives us the instantaneous rate of change, which is the derivative f prime of a equals limit as h approaches 0 of f of a plus h minus f of a all over h. So the derivative represents the slope of the tangent line, or the instantaneous rate of change of the function at x equals a. Now, in many situations, if h is very small, the average rate of change over that small interval is very close to the derivative. So we can write the approximation f prime of a is approximately equal to f of a plus h minus f of a all over h. This tells us that for small values of h, the derivative gives a very good estimate of how the function changes. Now, let's rearrange this equation to solve for f of a plus h. First, multiply both sides by h. And the h cancel out. And we have h times f prime of a is approximately equal to f of a plus h minus f of a. Now, add f of a to both sides. We have f of a plus h times f prime of a is approximately equal to f of a plus h. This formula is very important. It tells us that the value of the function at a plus h can be estimated using the original function plus the average rate of change times the change in x. This idea is called a linear approximation. Now, let's look at the graph. The blue curve represents the function f of x, The point a comma f of a is our starting point. Now, we move a small distance h to the right, reaching a plus h. The true value of the function there is f of a plus h. But instead following the curve exactly, we can approximate the value using the tangent line at x equals a. The tangent line gives us the estimate f of a plus h. If h is small, the tangent line provides a very good approximation. The small difference between the actual value and the estimate is called the error. Let's summarize the main idea. The amount of change is f of a plus h minus f of a. The average rate of change is f of a plus h minus f of a over h. The instantaneous rate of change is the derivative f prime of a equals limit as h approaches 0 of f of a plus h minus f of a over h. When h is small, we can approximate the function value using this formula. This idea of using derivatives to estimate function values is extremely useful and will appear often in calculus.